About the should I start?
Yeah.
Well, my question is, I think there was some sort of service over there. You know, the Society of American and NGS and all this stuff, and they're saying that not only the intern is
Sorry. Okay, go ahead.
Let's start from the beginning.
Oh, goodness, yes, you should.
Okay, so my question is, what is the reason, not only the New Orleans, that Louisiana is entirely thinking, what is the reason behind it? If the sea level is rising, that's the reason, or there is some sort of sedimentation or all this stuff, what is happening? What is the reason of Louisiana sinking?
Why is it subsiding?
Yes,
Yeah, because it's a bunch of brand new sediment that's loading the ground, so you dump a bunch of sediment at the, the end of the river, at the mouth of the river, and that added weight pushes the ground down. And there's faults all along the Gulf Coast. This isn't just New Orleans. There's these, what they call growth faults along the Gulf Coast, where you can see how the ground is like breaking as it's getting loaded by the sediment. The rivers going into the Gulf of Mexico used to have a much bigger sediment load than they have today. And the ground, the geologic setting is still adjusting to all of that sediment that was dumped like 5,000 to 20,000 years ago in the Gulf of Mexico. So it's something that's, bigger than just what's going on in New Orleans. It's the whole Gulf Coast is sinking, subsiding under the weight of that new sediment, and it's coming to equilibrium set of conditions. In New Orleans, you've got the sediment up until about 1930. The river was dumping quite a bit of sediment right in the vicinity of New Orleans, and we've taken that away now by analyzing the river, but the ground is still coming to equilibrium under that weight that was added hundreds of years ago. Yeah. Now, on top of that, you've got some pumping. So there's groundwater pumping, and this has been in the news a lot. The sea level rising and the salt water is pushing further inland, so it's fouling pumps and things. And then you've got oil and gas wells, which are also reducing pressures, and when you reduce pressures, you increase effective stresses, which means you're adding more impetus for the ground to subside. But the biggest source of it, as far as we can tell, is it's in the upper roughly 100 to 150 feet, and it's probably mostly just due to the sediment still coming under equilibrium under its own weight. It's not so much the oil and gas development that's causing the subsidence that we're seeing. Okay, so here is Hurricane Katrina. Here it is in the early morning of August 29th as it's making landfall. It is spinning in the northern hemisphere like all cyclones in a counterclockwise direction. So it's shoving, you can imagine the wind field shoving the water up onto the Gulf Coast. Here's where that really high storm surge was measured, more than 33 feet above sea level. It is shoving the water as well to the west. So it's shoving all the water into Lake Pontchartrain. So the whole east bank of the Mississippi River and Lake Pontchartrain on the north side of New Orleans is feeling the effects of this storm surge.
I got you.
Thank you.
Yeah.
And here is that storm surge. So here the water is coming up over the top of a levee. This is along the Gulf Intercoastal Waterway, just east of downtown New Orleans. For those of you familiar with the area, New Orleans East is in the foreground. There's an Entergy gas plant that's got a security camera, and that's how we have this picture. 41 is going over the Gulf Intercoastal Waterway into St. Bernard Parish, and the bridge piers you can see, and this is the levee that's part of the hurricane protection system, and this is the water that's crashing over that levee. So you have an unprecedented storm surge, and then like we talked about, turns out the system was actually built lower than it was intended to be because the ground is subsiding. So those two together mean for most of the system, the storm surge was way up above what it was designed for. And unfortunately, even though it wasn't designed to withstand that kind of storm surge, it for the most part actually did remarkably well, except in 50 locations, over 350 miles. So let me put this in context, but in 50 locations, breaches opened up in the system. And the real challenge now is not so much the breach allowing the storm surge to come in, it's that now there's a direct connection between sea level and 80% of New Orleans, which is below sea level. So this picture, this is actually from Hurricane Rita, but this captures the situation very well. To the left is the industrial canal. So we're looking north. On the east side of the industrial canal is the lower Ninth Ward. So that's what the land on the protected side is over here where that school bus is. You can see the water level in the industrial canal, that's sea level. You can see how low the ground surface is relative to sea level, and you can see the ocean water just dumping into the protected side through that breach in the hurricane protection system. The damage was catastrophic. I was part of a panel, and one of my panel members had toured Europe in a helicopter right at the end of World War II, specifically Germany, after it had been bombed significantly. And he was in this helicopter, and his comment was that the damage caused by Katrina was an order of magnitude more than what he saw in Germany right at the end of World War II. Hundreds of thousands of homes destroyed, businesses, cars. The University of Texas, we went over multiple times after Hurricane Katrina to help families. We met one family, I remember them very well because the son had a Michael Jordan jersey, and I'm from Chicago. That's great, but when we first went into his house, in his bedroom, the Michael Jordan jersey was still hanging in his closet. He had left on the Saturday before Hurricane Katrina made landfall, excited because he wasn't going to have to go to school on Monday. He's going to go get to see his relatives in Mississippi. So he didn't take very many things, including his Michael Jordan jersey. And when we walked into his house, it's the first time he had been in his house in a year since Hurricane Katrina. So he had no idea when he left on that Saturday that it would be a year before he would go back into his home, and his home was just totally destroyed. When we went back in it, we had to gut it all the way down to the studs, and ultimately the family decided to never move back. So on that Saturday when he left, not only did he leave behind his Michael Jordan jersey, but he left behind all of his friends, his school, his neighborhood, never to come back again. He never had that community again. So the scale of this, when you get down to individual people, is really catastrophic. And this is that boy's house, and that's what it looked like a year after Hurricane Katrina. Next slide. And like in Hurricane Betsy, people, as the water level rose, they climbed into their attics, and as the water level kept rising, and as it became really hot and really stuffy, in order to get out, they had to break out through the roof. So you see that hole in the roof there. This is along one of those outfall canals. This is called the London Avenue Canal. And
this is the, I'm so sorry to interrupt. So this is the amount of sedimentation that has been brought by the storm surge?
yes, not exactly. So this is along one of those outfall canals where there was an eye wall, and underneath this is called the Gentilly Ridge. So the Gentilly Ridge runs along kind of east-west, just south of Lake Pontchartrain, and it's sand. So this eye wall underneath it had sand, and as the storm surge rose up in the outfall canal, the water started running underneath the eye wall through the sand, and a piping failure developed. So the pore water pressures inside that sand layer got high enough that the wall essentially liquefied. The wall was no longer stable and the whole thing just ended up pushing up into the ground. So that's the sand that used to be underneath the eye wall and ended up in their front yard after the hurricane. Next slide. And 2,000 people lost their lives. Next slide. So the Corps of Engineers was charged with making sure this never happened again in 1966, and then it happened again. Why? Everybody was asking why. A group was put together called the Interagency Performance Evaluation Task Force. So interagency means it's all the federal government, it's NOAA, it's FEMA, it's the U.S. Army Corps of Engineers, it's the Bureau of Reclamation, it's everybody who has something to do with hurricanes and flooding and infrastructure to try to withstand these kinds of events and response to emergencies like this. And it had about 120 people on it. And many of them either were employees of these agencies or they were consultants who were hired by these agencies. So for example, one of my colleagues at the University of Texas, Steve Wright, who's a geotechnical engineer, he was a consultant to the Interagency Performance Evaluation Task Force. The best way to learn about what I'm talking about and much more about what happened in Hurricane Katrina is to go to the IPET website. So if you Google IPET, you'll find all of the reports and all of the data and everything that was put together in response to trying to figure out what happened and why it happened. There were two external groups put together because the public wasn't very believing of the federal government at this point after Hurricane Katrina, to make sure that whatever they came up with was credible, was defensible. One of those was put together by the National Academies of Engineering and Science. It had about 10 people on it. The other was put together by the American Society of Civil Engineers. That external review panel had 14 people on it. I was very fortunate to be a member of the ASCE external review panel. That's how I know what I know. And our job was not only to make sure that they did a good job in figuring out what happened and why it happened, but that it gets out, that people learn from this. And so that's one of my objectives today, is to let you all know what we learned. And what did we learn? Yes.
I was gonna ask you about the public forums, how many of those actually around the time that this happened? Once you all got the findings?
Yeah, a lot. I don't know how many, but yeah, I personally have just done something like this probably 50 or 60 times in the last 18 years since Hurricane Katrina.
Okay, thank you.
So what did we learn? I'm not going to get into the details, and I'm happy to answer questions about details, but I'm really going to look at the bigger picture, which is what actually went wrong. Number one, there was no evidence that the design did not follow the standard of practice. There were no calculations that were not done correctly. There were no models that weren't used correctly. There was nothing that we found that violated the standard of practice. There's some things we found that we learned. So like these eye walls and how they behave, we now limit how high the eye wall can get up above the crest of the levee because of what we learned from Hurricane Katrina. But that wasn't widespread knowledge before Hurricane Katrina. So Hurricane Katrina had a benefit in that we've learned and we're doing better in design. But if you look at it as of the time that that system was designed, there's nothing wrong with that design. It's as simple as there are places along that system where the storm surge was 3 feet, 5 feet, 10 feet above what it was designed for. That it's just, you know, I hope none of you design a system and then it gets loaded way beyond what it's designed for. But I think you always need to keep that in mind. And, you know, when you're calculating factors of safety and things like that, like that doesn't mean it's going to be okay. If it gets loaded beyond what you're thinking it's going to get loaded when you're designing it, you know, it's something to consider. In this case, it was not conceived of that way, so all bets were off when it got beyond what it was designed for. The second thing was there was no evidence that it had not been built properly. There was a lot of allegation that the contractors had cut corners, that there was bribery, that there were nefarious things going on in New Orleans, like there always is in New Orleans, and clearly people were on the take and not building this thing properly. We found no evidence of that. There was a specific example of that, one of the eye walls. So those sheet pile walls, there were these allegations that it was shorter than what it was supposed to be according to the design drawings. They did some non-destructive testing. This is a warning about non-destructive testing that indicated maybe it was shorter than what it was supposed to be. So they actually went and took a crane and pulled the thing up and out of the ground. And everywhere they did that, the sheet pile was longer than what it was designed for. They found nowhere where it was shorter than what it was designed for. What we did find was that there was a failure to plan for failure. There was a failure to manage the system as a system. There were a bunch of pieces and parts, different parishes, different water and sewerage boards looked after different things. The railroad looked after one thing. The highway department looked after another thing, but there was no coordination. They were not at all thinking of it as a system, even though it was called the Hurricane Protection System. There was a lousy job to communicate risks to the public. So there were 500,000 people in New Orleans. Only 400,000 of them evacuated before Hurricane Katrina. That meant there were 100,000 people in harm's way when Hurricane Katrina made landfall. In some ways, it's remarkable that only 2,000 people lost their lives. The decisions that were made, like to keep the benchmarks the same, that was not communicated very well at all to the public. In fact, no one really was aware of this. We had to go digging and find the letters from the 1980s where that decision had been made and had been documented. The system itself. So these outfall canals are the best example of this. They're like daggers that go right into downtown New Orleans. Why would you design a system so that the storm surge can come into Lake Pontchartrain, can come down these outfall canals right into the heart of New Orleans and then potentially flood the area? It's not because that's what the engineers wanted. The engineers, when they conceived of the system, actually had a gate that stopped the storm surge from ever getting into Lake Pontchartrain. And then they had gates because there were concerns about that and how it might affect the environment, legitimate concerns, and also the cost of that. The next version of it had gates at the south shore of Lake Pontchartrain so that the water couldn't get into these outfall canals. But the city of New Orleans fought that. And this is an interesting, when we talk about our code of ethics and how we play a role as engineers, this is what happened. Those outfall canals are used 24 hours a day to pump water out. They're very important to development in the city of New Orleans. And those outfall canals had a capacity that was limited, not by the pumps. They're some of the biggest pumps in the world, but those pumping stations were limited in how much they could pump by the capacity of the outfall canal. And the only way to make the outfall canals have more capacity would be to raise the walls on those outfall canals higher. And the only way to do that, because this is part of the city of New Orleans, would be for the city of New Orleans to pay for raising those walls higher. And the city of New Orleans didn't have a lot of money and didn't have the resources to raise those walls higher. So they fought the Corps of Engineers to not put gates at the end of the outfall canals, but to make the outfall canals part of the hurricane protection system, because then it would be part of the federal system and it would be funded by the federal government. So those walls that go down 3 miles, in one case 5 miles, in another case into the heart of the city, they were there because the city of New Orleans said, we want those walls there, and they got what they wanted. Now, I don't know that we could have changed that decision, but I don't think the engineers did a very good job of explaining clearly what was going on and what the downsides to doing that were going to be, nor were they a part of coming up with solutions. There's a lot of solutions beyond making it part of the hurricane protection system that could have allowed them to increase the capacity of those outfall canals. So the last part about this is what we didn't do is the stuff that we don't really learn so much about in school, right? Because we learn how to do calculations and learn how to develop design plans and specifications and monitor construction and all that stuff. That was all good. It's the part like working with the public and talking to people and helping decisions be informed. That's where we did a lousy job. Next slide. So a couple of lessons that I specifically took away for this. One is to think about what can happen if it fails. Ever since this project, every design I work on, very early on, we have a conversation about, well, what if the loads are greater? What if this thing is loaded in ways we never thought of? How is it going to fail? And can we make it so that it fails in a more graceful way versus a brittle, catastrophic way? The wall failures are a good example of this. So these flood walls, they had the water behind them. In one case, the water was coming over the top of the flood wall. This is on the east side of the industrial canal. The water coming over the flood wall eroded the soil on the downstream side of that flood wall, eventually weakened the foundation so that the flood wall collapsed. And that unleashed a wall of water that went into the lower ninth ward. It took the homes in the first block east of the industrial canal off their foundation. It shoved them into the homes in the next block east of the industrial canal and shoved them into the homes 3 blocks in from the industrial canal. And at the end of Hurricane Katrina, 3 blocks in from the industrial canal in the lower ninth ward was a pile of homes that had all been shoved off their foundations by this wall of water. That happened not because of Hurricane Katrina, that happened because of us. If we didn't have that wall there, the water just would have come in and slowly risen like it did everywhere else. The only reason that it was so catastrophic there is because we had this wall, we were trying to hold it back, and then when we couldn't hold it back anymore, and it gave way, this wall of water had created havoc. Storm surges aren't like that. Storm surges come to our tide. They come in over like 24 to 36 hours. In Hurricane Ike in 2008, it was really 48 hours. So they get slowly, the water rises. They're not something you need to run from. There's not a wall of water that's behind you in the movie screen. It's not dramatic like that. The water just slowly gets higher and higher and higher and higher and higher, and then it goes back down again as the water drains back out into the ocean. So by putting things to try to stop the storm surge, we made it even worse than it would have been if we had just let the storm surge come in and the storm surge go back out and then tried to drain the water that was trapped in the area. So that's a good lesson in, think about if it goes wrong, are there things we can do in our design so that it's not going to be catastrophic? Next slide. The system. So this is where, there were all sorts of examples. Many of the breaches happened at a joint between, say, a concrete apron for a gate structure and an earthen levee coming up against that concrete apron. So that's a classic kind of situation where you've got preferential flow that's running along that concrete apron through the earthen levee. And if you get a big water flow trying to go along that preferential flow pathway, you end up with internal erosion and you end up with a breach. There were also lots of examples between people in this system. So there's one location in New Orleans East by the airport where there were 2 gates right next to each other. They're like 20 feet apart from one another. So these gates are there because hurricanes don't come that often, but you need roads and railroads and things moving through the area. So whenever there's a hurricane coming, they come along and they drop gates into the system so that it's continuing. Well, the parish dropped their gate in, but the railroad's gate was broken, so they didn't drop their gate in. Did it matter that the parish dropped their gate in? No, it doesn't, because the water's just going to go right through the railroad's gate to get to the protected side. So there were lots of examples of that. These pumping stations, they are some of the biggest pumps in the world. They would have been incredibly valuable in the aftermath of Hurricane Katrina if they were available to pump all that water out. But the pumping stations weren't designed for storm surge. They were designed to pump the water the other direction. The storm surge came in, The backflow flooded the pumps. It took out the pumps, the electrical systems were on the ground floor, it flooded the electrical systems. It totally destroyed these pumping stations, so they were not available in the aftermath of Hurricane Katrina. Some of them, it took more than a year before they were able to repair the pumping station so that it could operate again. So they were not designed for this, even though they were very much a part of what we would call the hurricane protection system. Next slide. So assess, communicate, and manage risks. This is the best example I can give of this. The offshore oil and gas industry was subjected to Hurricane Katrina as well. It was a monster storm. It loaded lots of platforms beyond what they were designed for. I don't know why the bottom isn't showing.
Yeah, video thing, I don't know how to make it minimize. But it says 100 evacuations and 0 fatalities.
Yeah, that's the punchline, and you can't see the punchline.
Yeah.
Okay, well, so offshore, the platforms had all the same things happen to them that happened onshore. They got loaded beyond what they were designed for. Some of them survived unexpectedly. Many of them survived unexpectedly. Some of them failed catastrophically. Some of them were loaded just up to what they were designed for and failed unexpectedly, just what happened onshore. And property damage, it was the exact same. There was $30 billion of reported property damage offshore, and there was $30 billion of reported property damage onshore. So very similar situation. However, offshore, the 50,000 workers were evacuated successfully. No one lost their life. Onshore, the 500,000 people were only 80% evacuated successfully, and 2,000 people lost their life. There are a lot of ways of managing risk. I think as engineers, we tend to think in terms of, protection, like protection means a bigger wall, a stronger wall, a higher levee, a bigger pump, the kinds of things we learn about in classes. But maybe the best solution is to not do all of that and just invest money in evacuation. Maybe if people could take their pets with them. Now, I don't know how much money it would cost. I bet it would cost less than building a bunch of big walls and pumps, though, so that they're more willing to evacuate. Maybe if we could put them in a place that has air conditioning and clean water and is comfortable instead of the New Orleans Superdome, where there isn't water and there isn't air conditioning. I think there's a lot we could do with the kind of money it takes to build a system like this, and maybe more effectively manage the risk than by building more infrastructure to try to protect the people. Next slide. So, while I think that's not what happened, it's no longer called the Hurricane Protection System. It's now the Hurricane and Storm Damage Risk Reduction System. So it doesn't sound as clever, but it's supposed to be clearer that it's not protecting, it's reducing risk. The risk they're talking about reducing is property damage, not life loss. So you're still supposed to evacuate if a hurricane is coming to New Orleans. So this hurricane and storm damage risk reduction system cost $17 billion. They basically finished what used to be called the hurricane protection system. So they closed the perimeter, they built it on the West Bank, which is really good because Hurricane Ida loaded that system not long ago, and it performed very well. They raised everything up to what the elevations were supposed to be, accounting for subsidence. They built it to last for another 50 to 100 years, depends on where you are. So they've accounted for how much subsidence there is potentially going to be. They did not design it to account for sea level rise because the federal government told them they couldn't do that. This would have been the Bush administration. So, this is the engineers again in their cubicles, like solving the problem. They essentially accounted for it, they just didn't explicitly account for it. So they used factors of safety so that implicitly they built it so that if projected sea level rises happens, it's still going to be hopefully about where it needs to be in the next 50 to 100 years. But it's $17 billion, and You know, I don't know. I don't know that that was the best use of us spending $17 billion. But it looks nice and so far it's performed well. We'll see in 40 years. We'll see how well it's maintained. The best thing I think about it is not the walls. It's that the system is now in place. So there's a group that specifically looks after the whole system, and all the parishes and the sewerage boards and the railroads and everybody else reports to the same group. And they're responsible for making sure that all the gates are put in place, that all of the transitions between the system are effective and maintained and looked after, that the pumps are designed not only to push water out, which they always need to do almost 24 hours a day in New Orleans, but every once in a while, every 10 years or so, when a big hurricane comes, they're also designed to be able to withstand the storm surge. So it's now being operated like a system. I hope in 40 years, it's still being operated like a system. That's probably the most impactful thing that's different now than in 2005. Next slide. And here's an example of why this is such a challenging problem. On the left-hand side is the Teton Dam. That's in Idaho in 1976. It had a breach. The first time they filled the reservoir, there was erosion that occurred along the abutment. It's an earthen levee up against a rock wall. So it's just like those aprons in the hurricane protection system. The preferential flow along that interface created internal erosion and a breach. The breach released the reservoir. 11 people lost their life. There was one breach. That failure prompted the U.S. Bureau of Reclamation to issue new guidelines, new standards in how dams are designed, maintained, and operated throughout the United States. And at the time of Hurricane Katrina in 2005, there were a lot of people that said, hey, levees are just like dams. We ought to be using the same U.S. Bureau of Reclamation standards for our levees as we do for major dams in the United States. That's easy to say, but in scope, you know, the Teton Dam was less than a half a mile long. The hurricane protection system is 350 miles long, and it's not the only levee system in the United States. There's levee systems in Long Beach, California, and the Delta of California, and Miami, and Corpus Christi, Texas, and Houston, Texas, all over the place. There are levee systems like this. To say you're going to design all of them like we design a dam is just not very practical. We don't have the kind of money to be able to do that. The hurricane protection system had 50 failures, not one failure, and 2,000 people lost their life. So it's not as easy to just say, oh, we're going to design all these other systems to be that much more robust. Next slide. And where this puts us is kind of in the middle. If we really want to do a good job, if we want to fulfill our ethical obligation to hold paramount the health, safety, and welfare is the real important word here, of the public, the only way to do that is to work with others. We've got to be working with sociologists and psychologists and policymakers and economists and the owners and the operators, and ultimately the people who are going to be affected by what we do, both affected by the costs that it takes to implement the things that we come up with, and also by the consequences if something doesn't go well with the engineering systems that we come up with. And the challenge, if you go to the next slide, is that that's kind of how it feels when you get in the middle. And I felt this in 2006 when we would go to public forums in New Orleans. We're not overly happy with engineers. They were not pleased with anybody who had any connection to the U.S. Army Corps of Engineers. They were very skeptical. If you type my name and type, I don't know, what is the name of the group? I can't, levees.com, type levees.com, you'll find all sorts of nasty things written about me. You'll find a video made by John Goodman, Roseanne Barr, John Goodman, where my group is depicted, and we're taking a bunch of money from the Corps of Engineers in a suitcase. So it was difficult. It was many times, you know, I'd be afraid to read what had been written about me, very uncomfortable. So you can do two things. You can either hide and say, I'm not gonna do that again, I'm never gonna get in the middle of that again, that was really, really uncomfortable. Or you can do what I think we need to do as engineers and say, yeah, that's what happens. Like, if you really wanna be in the middle, if you really wanna do a good job, if you really wanna serve the public, I don't know how you don't get in the middle. And so one of the things I'm hoping that we as a profession are learning from this is that we need more of us running for public office. We need more of us going to community meetings. We need more of us working for municipalities. We need more of us being public servants. We need more of us that are just in our spare time volunteering our time to help the public. Next slide. And I have one example of that. One of the people I worked with ran for public office, ran for the water and sewerage board in one of the parishes in New Orleans, was elected successfully, did good work for about a year, but unfortunately really did not like being in the spotlight and all the negative things that were happening, and so ultimately stepped down. But we need more Tom Smiths. His name was Tom Smith. We need more people, Tom Jackson, sorry. People like that who are gonna run for public office and gonna be willing to deal with the criticism, because that's just part of the job. It's not personal, it's just part of the job. Next slide. And so ultimately, these are the lessons that I learned. I think where we've taken this in our curriculum is we've tried to do much more around public service projects and having engineers work on problems that are real problems out in the community and working with stakeholders in order to learn what's going to be best to help the public. But I think, you know, that's one little place that our whole profession needs to do a better job of that going forward. So with that, I'm happy to answer any questions that you all have. You had lots of questions in the break there.
I have one question.
Yes,
So, are we prepared for the next one?
I don't know.
Can you repeat the question?
The question is, are we prepared for the next one? I hope so. I hope so, but you know, and I'm 58 years old, and it seems like the next one never looks like the last one. So I'm sure things are going to happen that we never anticipated. I think, you know, one of the lessons for me is things fail. Like, it's not, I shouldn't walk around thinking things aren't going to fail and I'm a failure if things fail. Like, things are going to fail. That's okay. We need to learn how to make it so that when things fail, it's not as catastrophic as otherwise. I think that's the way we need to think. But if we get that everything has to be perfect and everything has to be successful, I think we're setting expectations way too high. It's unrealistic, and then we're going to do silly things that aren't actually going to do a good job of serving the public. Back here, there was a question.
Yeah, I wanted to ask, like, with increase in sea level rise and temperatures, or maybe climate change, the system designed to protect New Orleans, are they adequate now? Or was that involved in the designs as well, for the future storm?
Yeah, so this is where I'm going to get a little political, but we could not do that. We couldn't account for sea level rise. We couldn't account for potential climate change because the federal government forbade the Corps of Engineers from doing that in the design of the new system. However, what the engineers and scientists did was they implicitly did that. So they did do modeling. They did do analyses of what they think the sea level might be, what the frequency and intensity of storms might be. They accounted for that, and then they kind of put in factors of safety on things that they were explicitly designing for that implicitly accounted for some of that. I think today they wouldn't have their hands tied like that, and they could be more explicit about it. So the answer is they did do it, but don't tell the Bush administration that they did it. Yes.
So you mentioned that when were not part of the design because it was very proposed at the time, the previous fair, but the storm was not part, right? So the blame is not for the design for the engineers because they were limited by the code. But in the future, if the storms are getting stronger, so I'm not getting political, but in that scenario, who would be, I mean, where would be the blame? I just want to see what's your take on that.
Yeah, so what we did was we made overtopping part of the design of the new system. So it's not only designed to keep the water out up to a certain elevation, it's designed to be able to withstand water going over the top and the erosion potential of that water going over the top. Now, we'll see if it succeeds or not, but there's now an explicit design check. It was interesting, like the worst case is not the water being the highest over the top. The worst case is when the water's like about 6 inches over the top. That's when it's the most erosive. You know, the simplest example of that is down in Plaquemines Parish. The water was way over the tops of the levees and it filled in the water in between. So pretty soon the levees were just underwater and there was no erosion potential. So that there's like a sweet spot where you really have trouble, and it's, you know, intentionally been designed to be able to withstand those erosive forces. There's been some conservatism built into that, so I'm fairly confident it's gonna do well, but we'll only find out the next time the water gets open over the top of it, how well it does. To me, it's amazing that of the hundreds of miles that had that happen, so little of it actually breached. You know, another amazing part about it, we tend to look at the negative and not the positive. In Hurricane Katrina, the 17th Street Canal is the westernmost outfall canal. And on the west side of the 17th Street Canal is Jefferson East Bank Parish with tens of thousands of homes. And, you know, that's where Metairie is, where I was at that meeting a couple days before Hurricane Katrina. The eye wall that failed on the 17th Street Canal could have failed on the west side instead of the east side. And it was about to, like, you can see the distress in the wall, all of the wall. It's 3 miles down to the pumping station and 3 miles back again. Both of those walls were under distress. It just happened to fail on the east side first, and then the water level dropped. The east side went into Orleans East Bank Parish, which already had other breaches, so there was already water filling it up to sea level, regardless of whether the 17th Street Canal breach happened or not. So if it had happened on the other side, not only would have Orleans East Bank Parish been flooded, but all of Jefferson East Bank would have been flooded. So there's a lot of like good news things that happened. The system actually performed remarkably well, given it was loaded so far beyond what it was designed for. You know, but it's a very non-redundant system. So if there's one breach that opens up in one parish, doesn't matter if there's 10 breaches, you know, once you have one breach, it's coming to sea level.
So there's a question on Zoom from Dr. Kevin Boyd, my former supervisor at CTI. He says, others have used the tragedy of Katrina to argue more resilient systems are superior to more robust designs. You mentioned more resilient services to help people after a disaster. What can engineers do to effectively advocate for resilience?
Yeah, I think number one, we can tell stories about what happens when you don't. And number two, I think we need to ask the public what actually would help. I don't think I would have understood the reluctance of somebody to evacuate because they couldn't take their pet till you actually talk to them and say, well, why is it that you didn't evacuate? And when you find that out, then you can, you know, like all engineering problems, if we don't know what the problem is we're trying to solve, it's hard for us to come up with an effective solution. So I think a lot of it's going to require talking to our stakeholders and better understanding what actually really would help and what wouldn't help, instead of us kind of hypothesizing what we think an engineering solution might be. And it might not look like what we would have come up with all on our own, and we need to be open to that.
I have a question.
Yes.
So, when Hurricane Katrina actually, had a landfall over there, I think, from the entire floodwall, it was just like 60 to 90% was complete, and if the entire one was not complete at that point. So if I'm an engineer, so over there, I'm just taking a point of view of it. What are the things that as an engineer we can take as an action? Because it may happen that I am in a project right now, I'm going on a project and it's about half done. And something just like Hurricane Katrina is, having a land. What are the things that as an engineer, we can take some measures so that, the half done works are not become so serious, something just like that Hurricane Katrina has done for the projects.
Yeah, to me, the simple answer is communication. I think we need to be very clear and we need to work with people that know how to get messages out. That's not what I learned in school and how best to convey those messages, but the public needs to understand if the system hasn't been built yet in their area, they need to understand what the consequences of that are. If the system has been built in their area, but it's not designed for every storm, it's only designed for the 100-year water elevation, the public needs to understand that it may get loaded beyond what it was designed for, in which case you better evacuate. It's not there to protect you from the hurricane, it's there to protect your property from frequent events that flood your property. That's what it's there for. It's a risk reduction system. It's a property risk reduction system. It is not a life safety protection system. So we need to communicate that clearly and in ways that are effective. And I don't know what that, I mean, I can say what I think, but you're standing there in somebody's backyard and they've got this 14-foot high concrete wall. It sure seems like it's protecting them, doesn't it? So it's hard to get that message across. I go back to showing pictures of what it looks like when it floods and sharing stories about what it was like when it floods to try to make it hopefully as real to people as possible. So it's not a hypothetical thing. This is a real thing that we're talking about. But I think that communication is the key, and I think working with people who are experts in communication and with sociologists and psychologists and others who understand how people interpret and how people make decisions is really important. We can't do it on our own.
It's all about the taking the initiative from a social perspective, evacuation and all of this stuff. So it's not related to that. Okay, these are the design parameters or design things that we can consider when the flood wall or something just like that was not finished entirely. That is there anything that we could have done or we can do something just like that apart from the social perspective?
I don't know. I mean, stepping back, I would ask, is it really best to try to keep the water out, or would it be better to figure out how to develop the land in a way that it can flood every once in a while?
I have a addition to that based off of my experience in the Netherlands. Specifically the making the land more I guess compensate for the hard structures. So we have the hard structures of the levees, and then we have, maybe soft structures where it's kind of embedded, like you said, into the landscape. There's a project in Texas that's called Room for the River, and they're basically connecting the area around the river to be able to flood to a certain extent. But instead of that area being like off limits, they're developing like a natural park around it too. So it's not just that it's all taken by the flood infrastructure. It's still available to the community to maintain that connection to the river, but there can be no homes built in that area. So I think that maybe that's one of the ways that we can respond to like building all this hard infrastructure and still protecting people, because who knows when you're gonna finish, what you're starting and things like that. And I think Dr. Khan, you were gonna.
Yeah, and homes that can get flooded. I think that's in areas where things can get wet, we ought to be building homes that can get flooded and you can clean them and dry them out and keep using them. Like sheetrock, you have to build homes out of sheetrock in some place where it can get wet. Yes.
Yes, Dr. Gilbert, I had several questions, but my major question was in terms of our homes, So basically in your story, you mentioned there are many people who the families, they lost their home and even they didn't come back, right? And in our building system is the way it is being built the involvement of the engineers are not there. Is basically done by anyone can build a home. They have to be a builder. They don't need to do any design or anything, And also in terms of like the way this is being managed, I don't see like any kind of responsibilities being given by the city. That they are supposed to do some kind of enforcement, and I had some personal experience asking some questions to some people, and they told me that the person I talked to, he's a builder, and he told me that we know far better than engineers, and this is how we do it. And I told them like some other type of system. They told me that it's never gonna work because this is how we do it. And that's the word he mentioned. This is how we do it. And even if you are trying to bring in new ideas, people is all depends on the market. So market, if they're not, the builders don't build, Now, do you think like any kind of activities can be added to make our homes more storm resilient? Because they're not storm resilient, they're not flood resilient, no matter what. Whatever we live. Even the home I live in, anytime I have a storm, I feel like, okay, so this is not being designed for this type of a storm. So we are just lucky, right? So do you think like any kind of intervention, ASC or any other engineering agency can do to kind of like going through the proper engineering analytics coming to our home?
I do. I mean, there's a lot of things your question is making me think of. So an example of that is after Hurricane Andrew in 1992 in Florida, because of the damage to a lot of the residential structures, they changed the building code and they require hurricane ties and things now that weren't required. And some of that's propagated, like where I build a home in Austin, I now need to put hurricane ties in because of that. So I think there are things with building codes. I think a key part of this is the insurance industry, because that's really where the money is, and that's where the costs are when something goes wrong. It's I don't know that the answer is building a house that can survive everything, or is the answer building a house that doesn't cost as much, but then I'm prepared, to do repair work and to do maintenance work when a storm does come along. It's not one or the other. I think both are possible solutions, but the insurance industry, it's a big part of that because that's where the money is that's going to allow us to have money available if something goes wrong to be able to easily fix it, or not if our policy doesn't allow us. The Hurricane Katrina, almost all those homes were not insured because they were not insured for water damage from the storm surge, even though they had homeowners insurance. It's crazy.
Yeah.
I mean, that homeowners insurance didn't cover that kind of.
Like the house always wins.
Yeah, and they could have. I mean, the insurance company rightly so says, well, there's a rider. You could have gotten that coverage, and they offered it. Like when they got their homeowners insurance policy, they saw that I could pay another $500 a year to have this flood insurance, but very few of the homeowners and even businesses have done that. Not covered. And you had said something about is it all this soft stuff and working with people in communication, or is it all this hard stuff with calculations? And what I would say is it's not one or the other. Like we still need to be fundamentally strong. We still need to know what's possible and what's not possible and what it would take and how much it's going to cost and what the alternatives are from an engineering perspective. And we need to be working with the public to figure out how do we do this in a way that's going to be most effective.
Yeah, I was also thinking about that. So I think you are discussing about the pumping stuff. So when the storm water is coming, pumping, some of the waters were pumping from the one side, and then that it was not at that moment was active or something just like that. I was thinking whether is there anything that as an engineer, if something happens, something just like that. So what are the things I could have done? Or engineers could have done?
Yeah, so the new pumping station, so like the West Closure Complex, which is an example of one of these on the West Bank, has been designed so that storm surge can be coming this way, and it can be pumping that way to keep the floodwaters from the rainfall. So, the worst kind of storm for New Orleans is actually not Katrina. It would be a Katrina-like storm that then stalls. And for days, like Hurricane Harvey in Houston, Hurricane Harvey in some places stuff like 60 inches of rain. If that were to happen in New Orleans, that's crazy, because the interior drainage system is not made in any way, shape, or form to be able to keep up with that. So these pumping stations, that's as an engineer, we can design them to be able to have water going both ways. That means putting the pumps at a location, so if water comes the way that it typically doesn't come, the pump's still gonna be okay and not lose its functionality. It means putting the electrical systems, up above where the water could ever be if something were to go wrong. I mean, there are things we can do, and we did do. It costs money. It's expensive to do all of that. But yes, there are very much, specific engineering things we can do and that we've learned from what happened. But so an example of Hurricane Ida, so, we keep learning. Somebody asked like the next time something different will happen. Hurricane Ida, part of one of the flood control risk reduction systems has a gate. It's a small ring wall levee that's protecting a community. And there's a little lake in there, and there's a gate to keep the storm surge from coming into the lake. And the gate is designed for the water to be pushing the gate like this up against the structure. From the storm surge coming from the south, like up through the vicinity of this community. And what happened in Hurricane Ida was that at one point, the location of the storm and the counterclockwise direction, the winds were pushing the water in the lake inside the community to the south and shoving that gate the wrong direction against that structure. And it wasn't designed for that. So the gate broke. And then when the storm surge came along, the gate wasn't there anymore to be as effective. So it was, we learned again. It's like, we need to think about water going from both ways. Even though when you look at it on a map, it's, the water coming from the Gulf of Mexico that we're worried about. So I think there's always going to be these lessons of things not behaving the way that we expected. And I think we're always going to be open to learning. Okay, so how do we design a gate so it can get shoved either direction and be okay?
So I have a small question, like all these structures or systems that are put there to protect the livelihood or the asset. These things are
To reduce risk.
to reduce risk.
Property
These
damage
things
risk.
are, these things are designed keeping in mind the data from last century, like 1960, 80, something like that. But as we are approaching, as the time goes by, we are seeing that there is a thing that's climate change. So these things are not supposed to not function so well because the data is changing. Based on the data which it was built upon, the data is changing. So we cannot redo this whole structure since it's gonna cost so much money and so much trouble. So what can we do? I mean, the structure that finished after Hurricane Katrina in 2005, the whole structure finished and they were compensated for the subsidence that you said, it cost around $7 million.
$17 billion.
$17 billion. Okay, but that should have a design expectancy of 50 years. But will it last 50 years? I mean, how the climate is changing or something like that. Then we again have to add weight or something like that. Because yes, if you to manage a disaster, we need the hard stuff and the soft stuff management. We need them both. But as an engineer, the decision-making part is always not in our hand. So how can we compensate with the design of these structures so that they can last long?
Yeah, I'll go back to communication. I don't know what other to do than to communicate clearly with the stakeholders about what it can do and what it can't do and what the costs are of making it different. I do think we should not think in this black and white way, like it's going to be okay if it's designed with 100-year water elevation, or it's not going to be okay if it's not designed with 100-year water elevation return period. The reality is everything can be subjected to whatever hazard, and it's a continuum. So it might not be any longer designed to the 100-year, maybe it's to the 80-year return period. Is that, catastrophic? The way our system works right now, it is, because all of a sudden now you can't get flood insurance, but it shouldn't be catastrophic. It's just a little bit of an increase in the risk from the 100-year return period. So I think we need to be more nuanced in some of the conversations we have. It's not that it's okay or it's not okay. It's that there's a level of risk reduction that we can manage. It costs this much to reduce the risk. We can gain this much by increasing the risk a little bit. Let's have a clear conversation about all of this, not it's okay or it's not okay.
So the little gray area in between, I mean, we have to like manage it.
Yeah, I don't think it's gray and I don't think it's little. I think it's very colorful and I think it's very big. Yeah, the offshore structures, they're all designed for the 100-year wave height. After Ivan and Katrina and Rita, the 100-year wave height, based on the data from hurricanes, because we only had like 50 years of good data where they were flying planes through it. The 100-year wave height went from 74 feet to 92 feet. The loads on the structure are proportional to the wave height squared. So the loads on structures for design purposes increased by 40%. None of those structures were designed for that wave height. There's 4,000 of them out there still sitting there. We had to have a really difficult conversation about, is it right or wrong or okay or not okay? It's not as simple as that. There's more of a risk now that we understand the hazard better. It doesn't mean we need to rebuild all these structures or raise the decks or abandon all the structures, but we as a society, the operators of those have taken on greater risk now. So there are different ways of managing that. Maybe they need a bigger insurance policy because it's more likely that they're gonna have hurricanes to deal with and damage to deal with because of those hurricanes. I know we're like way over time.
Over
aren't
30
we?
minutes, but Dr. Lee will be the last question. Dr. Lee is the last.
You said there are like 100,000 people who did not evacuate. What was the reason they did not? Because of infrastructure limitation or they are unwilling to, because they know the risk. I mean,
Yeah.
maybe they don't know.
So this is one of the interesting things about who lost their life and who really was impacted the most by Hurricane Katrina. The vast majority of them were elderly people. The vast majority of people who did not evacuate were elderly. The vast majority of people who lost their life were elderly. And why they didn't, I think there's some obvious reasons, they're more protective. They had ridden through many hurricanes in their life and never had a problem like this. They're less agile, maybe they're less mobile. But that's where, like, if we want to invest money in helping people evacuate, in addition to helping people bring their pets along, we really need to look at the elderly people and better help them. Yeah, but it's more energy. If you're in a wheelchair, it's that much harder to move from one place to another place. The property damage was not discriminating. There were really rich areas that had houses destroyed, and there were really poor areas that had houses destroyed, and it was, nature is not discriminating. What was discriminating is if your house is destroyed and you're well off socioeconomically, you can manage that fairly easily. But if you're not well off socially or socioeconomically, it could be like you never have a house again because you don't have the means or the wherewithal to be able to manage having lost your house. So that's where the impact is. It's the ability to tolerate when something goes wrong. And that's another thing that we as engineers can possibly help the public with, if we put our energy to it.
Okay, and now we're gonna have Rita come up. She has something.
We have
Thank
a
you,
birthday to
everybody.
celebrate, right? When are we celebrating the birthday?
Well, we have a presentation for you. Surprise.
Okay.
Okay,
Oh, is the birthday a surprise?
it was. It was.
I'm sorry, surprise.
But we knew, that's fine.
Watch
we
your
knew.
step.
There's the wine.
We can remove this one, right?
Thank you, everybody online from CTI. You all are amazing. So go ahead, Farida.
Is this for me or for the
This is for you. He's coming to you.
Oh, fantastic. Thank you very much. I really appreciate that.
And we're gonna ask Fahim to stand up now because it's two people's birthday and they just so happen to be married. And so we're gonna have Fahim step to the front. And you're gonna hold on to his stuff, or you can give it to him. You can give it to him. Dr. Gilbert, that's yours.
Oh. This was a birthday present.
Yours. Yeah.
Are you two the two birthday?
Yeah.
And you're married? Well, come and get a picture.
Yeah.
And I shouldn't be in it.
All right. Yes, we're gonna sing happy birthday. 1, 2, 3. Happy birthday. Happy birthday. Happy birthday. Okay, so we have lunch and we also have a presentation.
Birthday.
Thank you.
But, Dr. Khan and
Thank you.
Fariha, as you often walk by my office, this is your stress relief. And that's what that is.
Oh.
I don't know about that. No. And also, this is called Veteran Glow.
All right.
And like, oh.
All righty, and that is the end. I'm going to end this meeting. Sorry we couldn't send you all food, but I hope you all enjoyed the talk and.
Back there, you have,